So this lesson on transformations of graphs is essentially a review of the vocabulary and concepts that you learned about in Algebra 1 and Algebra 2 in how we transform graphs on the coordinate plane. And we're going to be transforming all different types of functions, but specifically today we're going to focus on the quadratic and the square root function because those are the ones that are easiest to translate so we can see what's going on here. The first type of transformation we can do is called a translation. Now translations, if you remember, are just slides along the graph. We're going to move it up, move it down, move it to the left, move it to the right. The very first transformation is a horizontal transformation, and if you notice, I don't know why my highlighter is so small. If you notice, this transformation for both directions appears when you're adding or subtracting numbers to your input, so inside the function. When you subtract a number on the inside of your function is going to move to the right, however many units you subtract. And if you add a number on the inside of your function, it's going to move to the left. If you look at the vertical transformation, so vertical is up and down, notice now that I'm not adding and subtracting numbers inside, I'm adding and subtracting numbers at the end of the original function f of x. When you subtract a number, it's going to move down, which makes sense. And when you add a number, it's going to move up. Pretty simple. So what this means is, let's say I have the quadratic parent function y equals x squared. If I want to move it to the right, I would subtract a number inside and it would move it to the right. If I wanted to move it to the left, I would add a number on the inside of that function and it would move the graph to the left. If I wanted to move it down, you'd subtract a number on the outside and it would move that parabola down. And if I wanted to add a number, sorry, that's a kind of ugly parabola, it would move it up. Pretty simple. In previous classes, you might have focused on getting the transformation vocabulary correct. I want you guys to focus on these formulas here. We need to be able to recognize and transform graphs using those formulas. The next type of transformation we have is a reflection. Okay, in layman's terms, these are flips. We're going to be reflecting or flipping our graphs across both the x and y axis. If you multiply a -1 in the very front of the function, y equals negative f of x, you're going to reflect it across the x-axis. If you reflect it over the y-axis, you're multiplying that -1 inside the function. So to view what these look like, let's use our handy-dandy square root function. The parent function of the square root looks something like that. If we want to reflect it over the x-axis, that means we're multiplying -1 in the front. Remember, this is the x-axis, so we are just going to reflect it over that x-axis. If we want to reflect it across that y-axis, again, we're just going to reflect it or flip it over the y-axis, and that would be that transformation. The last kind of transformations are stretches and shrinks. Now these are sometimes called dilations. You're changing the shape here. We're going to make them wider and narrower. Okay, now there are two types of stretches and shrinks we can use. One of them is a vertical stretch and shrink, and one of them is a horizontal stretch and shrink. We're going to spend more time looking at vertical stretches and shrinks than horizontal, but we'll talk about both. Notice this time that the difference between horizontal and vertical is where I'm multiplying my scalar. If I multiply a scalar in the front of the function, it is a vertical stretch and shrink. If I multiply that scalar on the inside, it's a horizontal stretch and shrink. Now, the kind of number that you plug in is super important here. So if you're multiplying by a number that's bigger than 1, so bigger than 1, 1.5, 2, 10, then you're going to do what's called a vertical stretch. Your graph is going to get narrower. You're going to take the top and the bottom of the graph and stretch it, which means it's going to get narrower. If you have a number that's between 0 and 1, what I'm calling a true fraction, I'm using air quotes because all numbers are fractions, but between 0 and 1, that's called a vertical shrink, and your graph is going to get wider. Okay, with the horizontal stretches and shrinks, you're multiplying that scalar on the inside of the function, and the vocabulary switches. If your number is bigger than 1, it's called a horizontal shrink, but it's by a factor not of c, but of 1 over c. And if the number you're multiplying is a true fraction, again, air quotes true fraction, between 0 and 1, then it's called a horizontal stretch, again by a factor of the reciprocal 1 over c. For horizontal shrinks, your graph is actually going to get narrower. And for your horizontal stretches, the graph is going to get wider. So the vocabulary switches, and if you stretched and shrank a picture of a dog, you took the top of it and stretched it up, it's going to get narrower. If you squished it down or shrunk it, it's going to get wider. Same thing horizontally. If you shrink it or make it smaller, it's going to get a narrower picture. If you stretch it, it's going to get wider. That's your transformation vocabulary. You're probably pretty familiar with the vocabulary, but I need us to get familiar with what I've highlighted, which is the transformation formulas. So some things we might have you do with these transformations is that we might have you write a function for each transformation. Okay, the first thing that I recommend doing is making sure you know what parent function you're working with. This is the quadratic parent function for the first one. And when we use the quadratic parent function, we need to designate what our inside is so that we know how to multiply things outside and inside. So if I'm doing f of x equal to x squared, I have to make sure that I know what's inside the function. This is a squaring function, so that means this x is on the inside. Okay, here's the things I want us to do to this function. I want to vertically stretch it by a factor of 4. I want to reflect it over the x-axis. I want to move it right 4 units and down 2 units. So horizontally translate it 4 and vertically translate it down 2. Okay, I recommend taking your parent function and giving yourself lots of space to do all of these transformations. Okay, if I want to vertically stretch this by a factor of 4, vertical stretch by its formula means I'm multiplying a number in front of the function. That number is 4. I'm multiplying it in front of the function. By its formula, a reflection over the x-axis means that I'm multiplying a negative 1 in front of the formula. Okay, done. By its formula, moving to the right 4 means that inside the function I'm going to subtract 4. Okay? And by its formula, to move something down 2, I'm going to take f of x and I'm going to move it down 2. Done. F of x equal to negative 4 times x minus 4 squared minus 2 has vertically stretched, reflected over the x-axis, translated horizontally and vertically, that quadratic parent function. If we check out the other 2 examples here, it's pretty obvious what the inside of the f of x equal x squared, or square root of x, function is. Obviously, there's the inside. So let's see, this time I'm going to horizontally stretch it by a factor of 3, reflect it over the y-axis, move it to the left 1, and up 7. Alright, let's set this up. We have f of x equal to, and then give myself some space. Now, I want to horizontally stretch by a factor of 3. Remember, this is the reciprocal of the number you see in the formula. And horizontally means it goes inside. So I'm actually going to multiply by the reciprocal of 3, which is 1/3 on the inside. To reflect it over the x-axis by its formula means I'm going to multiply by negative 1 inside. By its formula, to move something to the left 1, that means I'm going to add on the inside. And by its formula, to move something up, I'm going to make sure I add 7 on the outside. Please make sure that your numbers are either for sure inside or for sure outside of that function, like you see here. That plus 1 is for sure on the inside of the square root, and the plus 7 is for sure on the outside. Our last one, with the absolute value function. Again, it's pretty obvious what the inside of the function is. It's inside the absolute value bars. We are going to horizontally shrink this by a factor of 1/2, move it to the right 3, and up 4. Okay, by its formula, by its definition, a horizontal shrink will be inside and flipped the opposite. That means, oh, forgot my x, that on the inside I'm going to have a 2. To move something to the right 3 by its formula, you're subtracting that number on the inside. And to move something up 4 by its formula, you're just going to add 4 at the end. This f of x that we've written will be a horizontal shrink by a factor of 1/2, move to the right and up from the original parent function for that absolute value. Example 2 asks us to describe each transformation. Start by identifying the parent function. So what's the parent function here? This is a quadratic function or a squaring function. So comparing what I started with, this f of x equal x squared, with what's here, I have 1, 2, 3, 4 things that are different. Let's name those 4 things. By definition, if you're multiplying a negative in front of the function, that's called a reflection over the x-axis. By definition, because we are multiplying a scalar of 3 in front of that x squared function, that is a vertical stretch by a factor of 3. Okay, it's a stretch because that number is bigger than 1. If it had been a fraction, it would have been a shrink. Then minus 2 on the inside, by definition, when we're subtracting numbers on the inside of the function, is a horizontal translation. And this is going to move to the right, because subtracting numbers moves it to the right. It's kind of the opposite of what you think would happen. And if we add 4 at the end, that's a vertical translation. This is going up 4. Makes sense? Let's try the next couple examples here. For letters B and C, they both have the same parent function. Their parent function is, oh, that's a lie. They don't both have the same parent function, my bad. The parent function for B is the square root of x, and the parent function for f of x is the power function cube root of x. Sorry, I missed a 3. But if you look at number B, letter B, there are 3 things that are different from the parent function to my transformed graph. Let's name them. We're multiplying a negative 1 on the inside. That's called a reflection over the y-axis. We're adding 3 on the inside. That's a horizontal translation to the left 3 units. And since we're subtracting a number on the last little piece right there, this is called a vertical translation down 2. Makes sense? In question C, you've got 2 things that are different from the parent function of the cube root of x. One of them is multiplying a negative on the outside. That's called a reflection over which axis? Over the x-axis, cool. And then we're multiplying a scalar on the inside. Inside should mean it's definitely horizontal. And we have to remember if this is a stretch or a shrink. Okay, your big numbers, your numbers bigger than 1 on the inside are actually going to shrink it. It's the opposite of vertical. But the factor is the reciprocal by 1/7. Cool, so we can identify these transformations from different equations. Good to go. Our third example, this is when it gets really cool. We're going to describe how to transform the graph of f into the graph of g. We're going to write a rule for it too. So what we can do for these functions is we can compare them in a way that we're writing g of x in terms of f of x. So I'll color this one in red, and I'll color this one in blue. We're not composing these, so don't panic. But if I'm writing the g of x function, in terms of f of x. That means I'm taking the f of x function and doing something to it so that it becomes this x minus 2 on the inside. What would I have to subtract, add, multiply, divide this x plus 5 with so that there's an x minus 2 on the inside? Well, to get to negative 2 from a positive 5, I'm going to have to subtract 7. And if I do x plus 5 minus 7, I end up with that g of x function, which means that the rule that we're using here is that g of x is f of x, but we're going to subtract 7 on the inside. That's the rule. So now let's talk about the vocabulary. If we're subtracting 7 on the inside, that means that we are horizontally translating this graph to the right 7 units. And if we actually compared these two graphs, like graphing it in Desmos or in your calculator, you would see that the f of x function and the g of x function are separated by 7 units to the right. We just have to move the f of x function over 7 times to the right and we'd have the g of x function, which is pretty dang cool. Okay, I want you to pause if you're watching this video and I want you to try B and C. See if you can figure out the rule and the vocabulary used to go from B to C. So here's letters B and C. Both of them we just need to translate. We wouldn't have to reflect or stretch, but we would translate B 7 units to the left horizontally with that rule. And then for the other one, we'd have to vertically translate it because that number is on the outside. We'd have to vertically translate it up 7 units. So there's the rule. Pretty cool. So the last thing that we're going to do is we're going to accurately graph these and we're going to do these things by hand. Okay. First thing I want you to do on this page is I want you to change this cubic function down here to a squared function. We just need more practice with our quadratics because if we get really complicated formulas, obviously you can just graph it in your graphing calculator, plot the points and go. But I really want to nail down these two basic functions, quadratics and square roots, so you can see some patterns going on here. Before we get going, when we're graphing quadratics, there's actually a pattern we can use, and it has to do with literally the squaring function. But instead of actually squaring these numbers every time, if you remember that from the vertex, you go either right or left 1 and up 1, and then right or left 2 and up 4. That's going to help us quickly draw our sketch graph, accurately graph our parabolas on this coordinate grid, even when there's transformations involved. Okay, because that's for the original f of x equal to x squared function. We just have to decide how the transformations do to it. So if we look at this first one, we've got 1, 2, 3, 4 transformations from the parent function. Let's describe them. Well, the first one is a reflection over the x. The blue one, since it's multiplied in front, is a vertical stretch, which means this graph should get narrower by a factor of 2, and I want you to call that your scalar. That's what we're going to multiply by all the time. If you also, to reflect it over the x-axis, we're going to call that a sad parabola. Because the reflections over the x-axis, we should have a frowning graph here. If we subtract 2 on the inside, remember that's a horizontal translation. 2 units to the right. And plus 3 at the end is a vertical translation up 3. Now my translations actually become my vertex. So if you use these numbers, you can create your starting point or your vertex. Your vertex is right 2, up 3. Left would be negative, and down would be negative, but we went right 2, up 3, which means I have my very beginning starting place, over 2, up 3. There's my vertex. Okay, I can follow my pattern remembering 2 things. Number 1, that instead of going up because we have a sad parabola, we should be going down from this pattern up here. And every time we either go up and down, we're going to have to multiply it by this scalar of 2. So if I start at my vertex right here, and I'm going to plot my next point, I'm going to go over 1 and down 1, but not down 1. 1 times 2 is 2. So over 1, down 1, 2. That's where my next point would be. And then I can go over 2, 1, 2, down 4, 1, 2, 3, 4, but times 2 is 8, 5, 6, 7, 8. That's where my next point is going to be. I can go the opposite way. Over 1, down 1, but down 2 because of the scalar of 2. And over 2, down 8 to graph my parabola. Connect the dots. I want you to be really obvious with where your coordinate points are. Okay, so make them big and bold like that so I can see that you're accurately graphing these things. Again, I could have found a table of values and plotted the points, but that's boring. We have these formulas here. We have these ideas of finding the vertex with your horizontal translations and also the multiplication with that scalar and whether it's a sad parabola or a happy parabola. But let's back off for a second. Let's look at the second example. This one's not as crazy, and remember we changed this to a quadratic because we need more practice there. You've got 2 changes from the original parent function. Let's name them. Since there's a 2 in the front, we have a vertical stretch by a factor of 2, and a plus 1 on the inside means that I'm going to horizontally translate this graph to the left 1 unit. Now, again, this horizontal translation gives me my vertex. There's no vertical translation, so my vertical number is going to be 0. But my vertex should be at -1 or left 1, 0. And this scalar of 2 is what I'm going to multiply that pattern by. Remember, the pattern is over 1, up 1. But I'm going to multiply that by 2. So over 1, up 1, 2 is my first spot there. Big and bold. If I go over 2, up normally 4, because 2 squared is 4, but I'm going to multiply that by 2, so it should be all the way up at 8. I do the same thing going the other way. Over 1, up 2, because I'm multiplying that scalar by 2. And then over 2, 1, 2, up 8, because that's 4 times 2. And voila, I have my narrow parabola graphed accurately, maybe not smoothly, but accurately on this graph. The last function that we're going to graph here is no longer a quadratic. It's actually a square root function. And we know a few things about square roots. We spent a lot of time talking about them when we talked about the 12 basic functions. But this is a transformed square root function. It's transformed by a reflection over the y-axis and a horizontal translation to the left 4. Now, something interesting is going to happen here because we are reflecting it over the y-axis. It's going to actually look like this graph goes to the right, but that's because we have a reflection over the y-axis, so it's super duper weird, okay? Because normally you'd say left 4, so that's right here. But we're reflecting it over that y-axis, so we actually need to plot that point here, reflected over the y-axis. Wild, right? So not this guy, but yes, to the red dot. That's my translation left 4. Now, square roots have a pattern, but I think for us it's going to be easier if we just make a table of values. So let's plug in 0 because that's pretty easy. If we plug in 0, we're going to have -0 plus 4, which is square root of 4, which is 2. Okay, so I can plot the point 0, 2. The next time there's a pretty point, I'm using air quotes but you can't see me, pretty point for this graph is when I'm plugging in -5. And again, if you just wanted to keep plugging in points until you have a pretty point, that's fine. And this is pretty because we're plugging in -5 when there's already a minus, so that's like 5 plus 4, which is 9. Square root of 9 is 3, so -5, 3 would be my next accurate point here. And that seems like plenty for us to draw an accurate graph. This has taken what would have been my normal square root function, I'll graph it on there for you, something like that, and we have reflected it over the y-axis and horizontally translated it to the left, even though it looks like it's going to the right, which is wild. Transformations should be a little bit of a review and a little bit of extending some of the knowledge you have from before. So hopefully this vocabulary gets stuck in your brain and that you start to learn it. See you in class.